Welcome to Nonlinear Optics once again, the last lecture before Christmas. Well, you have seen and heard all the bad news from the last 2 weeks. Actually, it was 2 weeks ago that we had the last hybrid lecture here. Well, honestly, I think that it's very possible to have a safe hybrid lecture here. And I think the way we did it was actually safe. But what's probably not possible is to make sure that all the colleagues also do it as carefully as we did it. And so you see, it's not possible to verify and to make sure that everybody goes according to the rules. And actually, exactly this is the reason why we are in this situation in which we are. And I hope that you behave differently, that you also give a good example, a role model for others, such that we see better times soon. On the other hand, we shouldn't let go down our moods, so we should keep a stiff upper lip, as the British would say. And in order just to make this lecture a little bit more beautiful, I brought this Christmas tree, also 2 stars here. Hope you like it. And I have a cup of tea. So after 45 minutes, if I forget it, please remind me via the chat that we make 3 or 5 minutes of break. So here is, the tree is great. Yeah, so thank you. So last lecture before Christmas I said, what I would like to offer next week would be a Zoom meeting, just for a little bit of discussion. Starting at 12, I have another appointment at 1 o'clock p.m. So for an hour I would be available, and I would send a Zoom link around. And if you have time, I would appreciate if you join on Zoom. So now let's go on with this lecture. We have to complete what we started last time. Remember, we derived the coupled wave equations. I said that they are very important, and so on, blah, blah, blah. And then we said, let's look for a few, easy but insightful examples. And we had one which we actually kind of denounced as trivial, but actually it's not. Yeah? So we saw there the cornerstone of phase matching, and we'll come to that in a known chapter. We also saw the Manley-Rowe relations, which is actually just energy conservation. Yeah, we were assuming a lossless medium. And then we started this chapter here. It's chapter 4, I guess. Yeah, so chapter 4. We started this chapter, and there we said, let's assume that one field is very strong, such that if I convert a few photons, if I take a few photons from that field, that it doesn't change its amplitude noticeably. And this is the so-called undepleted pump approximation. So here is here is my script. I hope you see it. No? I think I have to do it like this. Yep. Okay, here is it. Yeah, chapter 4, the undepleted pump approximation. And well, this was simple enough actually, right? So we just took the derivative of the first of these coupled wave equations. So this one here, right? And so we took the derivative here and then substituted the other coupled wave equation into this, right? So and then we started to solve it, yeah, and we completed it almost, but not quite. So let's finish this today. And it's just a few lines. So the next point that we have to do here actually is to think about this factor and to calculate this factor. So calculate kappa over capital K1. Right, so this is apparently K1 here. Right, and this is the square root of this equation 4a that you see above here, divided, of course, through equation 1, which gives this K1, right, as you see here. Well, and this just has to be done. This is trivial. I don't want to do it in all the details because it's really just substituting the equation and then canceling out the terms that can be cancelled. And what you get is minus the imaginary unit times the square root of the refractive index at wavelengths 1 times omega 3 divided by n3 times omega 1, and then we have here the amplitudes, so the amplitude of this second field. So that's equation 9. It's of course clear that we now have to look for this term here, the magnitude of A2 divided by A2 star. What's that? What's that? Okay. On first glance, it looks kind of like a unit thing, right? But here in the denominator, we have the complex conjugate, and so what we get is the phase. So this is the next point here, that we calculate A2 magnitude divided by A2 star. And well, if you do this, then you would find, that this is the phase of this amplitude that we assume to be constant, right? So once again, so we assume that this is here is the strong field, right? And now, if you look at the solution that we got, right? Then you see that this field A2 doesn't show up in any of the solutions. Well, just a little bit indirectly through this phase. So it provides the right phase such that you convert the radiation in one direction or the other direction. Right? We'll see this. Okay, so this is equation 10. And with this equation 10, we are pretty much finished. Right, so the only thing is that we need to substitute this equation 9 and 10 into equation 8, right, which is the sum frequency, so the frequency or the color that we newly generated. So what we do is equation 9 and equation 10 into equation 8. And then we get A3 of Z is equal to I, so just equation 9 here, N1 times omega 3 divided by N3 divided by omega 1. And then we have the amplitude of the first frequency at the position Z equals 0, and then we have here sine of kappa times Z times, and now this phase, which is given by equation 10, right? So let's call this here equation 11. And then you remember that what we observe is actually not the amplitude, but the intensity. So we quickly calculate the intensity by taking more or less the square and divide it through, well, epsilon 0 and c or so. And this is then the intensity. So the intensity of this sum frequency. This is proportional to A3 of z squared, and this is proportional to A1 at position 0 squared times sine squared times kappa times z. So this is equation 12, and this is the final result. Let's look at how this looks like. So just we can just plot it. Yeah. So this is actually how it looks like. Yeah. So what we have here, so what we calculated actually is this one here. Yeah, so this here is A3 squared. This is proportional to the intensity, right? And on the other hand, we have this field, yeah, the photons of which the photon energy of which we increase. So remember, I told you what a typical application could be. Yeah, so we said that maybe this field A1 consists just of infrared photons that are difficult to detect, and then I would mix it in the way that we did, right? And then get the sum frequency out, which would be much easier to detect. Yeah, and you would see, yeah. So this goes here up very nicely. Actually, it goes up to the point where all of the photons in A1 in this presumably weak field are destroyed and converted into photons at the sum frequency, right? But then afterwards it goes the other way around, right? So afterwards the photons in A3 are destroyed and the photons at A1 are recreated. And so it goes, so as you go through this crystal, things go back and forth, so the energy goes back and forth between these two fields. Yeah, so this is actually an interesting figure, also from another perspective, because exactly the same mass you have for a very important problem in quantum optics. Any suggestions on the chat? So any suggestions what I mean? So I wait for 10 seconds or so, and I'm curious whether some of you know that. I said 10 seconds. Yeah, I wait 10 seconds. 10 seconds are over. Nobody? Did you hear of Robbie oscillations? Robbie oscillations? Yeah, so here's somebody answered. No real suggestions. Maybe entanglement. Yeah, entanglement is an interesting thing, but no, even simpler. So we have Robbie oscillations, and the problem. So Robbie was actually an American physicist, originally coming from Hungarian Austrian Empire, and. So what I will so he was a student of Max Born, right? And I'll throw in another name soon. This is Felix Bloch, and all of these three persons, very prominent persons in quantum mechanics and quantum optics, they all were of Jewish origin, and I just admire this culture. Yeah, so this small people. Bringing, so creating so many great scientists. So, and this is just another example. So this is Robbie, and he looked, so I wanted to show Robbie actually. Yeah, so here's Robbie. Isidor Isaac Rabi, very important physicist also for microwave electronics and so on. So Second World War radar technology. So you can imagine how important he was for the US. Yeah, so the German Empire, the Germans, or the European, particularly German culture at that time drove them away. So the problem he looked at in this case was resonance fluorescence. So consider a simple model of an atom where just two states are important, typically the ground state and an excited state. And now you shine in light at the resonance frequency. What happens if there is no spontaneous, so if you can neglect spontaneous decay, right? What then happens is exactly the same thing that we calculated. Physically, it has not much to do with each other, but the mathematics is exactly the same. Yeah? And so what happens is that you pump all the population up here, right? So this is when all the population is up there, but then you pump it down again, right? And so the oscillation, so the population oscillates between these two states. And it depends in the same way as we have seen here, it depends on the intensity. The more intensity you use, the higher the frequency with which this happens. And this is called actually the Robbie frequency, and the entire thing is called Robbie oscillation. Now to Bloch. Felix Bloch, a Swiss physicist. I think he was the first PhD student of Heisenberg. And later he was an assistant to Wolfgang Pauli. He invented a very nice way to see this, namely the so-called Bloch sphere. And here we have the Bloch vector, right? And if this vector points to the south pole, then all states, so then the system is in the ground state. And now you pump it up, and if it's at the north pole, then we are here. The interesting thing, or one of the major things, is if this vector is in the equatorial plane, then a lot of effects can happen, which are very important. For example, for magnetic resonance imaging. So photon echoes and things like that. So if you have no idea of what I just explained, then you know that there is a serious gap in your knowledge that you should fill at one point or the other, better sooner than later. So this is a fundamental thing of quantum optics. And here we have seen the same mass. Okay, what are the other curves here? The other curves here is if we are not quite in resonance. Right? So if we are a little bit detuned, if the photon energy is a little bit less or a little bit more than this energy difference, right? Then you get a faster oscillation, but also an oscillation with a smaller amplitude. Why do I say this? Well, because it's important by itself, but also because we have exactly the same thing for our undepleted pump approximation. So let's go on here, and actually I will not explain it in detail because it doesn't give so much insight, I think. So we do the same thing, some frequency generation in the undepleted pump approximation, with the assumption that the phase matching is not perfect. So that we have a phase mismatch, delta k is not equal to 0. Right? And then, of course, things are a little bit more complicated, and you see this here. Right? But, yeah, so one has to solve it, and I did it by Mathematica, and it's a few pages. but it's just mass, yeah? So not much physics, a little bit boring. And, well, what you see in the end is exactly the figure that you saw before, right? So this one here concerns to delta k is equal to 0, as you see here. And this one here, well, I think, hard to read for me, I think it means 4 kappa or something like that, right? So there's a delta k equal to 4 kappa. Good. This concludes this chapter. So we come to the next chapter, and well, the next chapter is also, so from a mathematical point of view, it's also a little bit technical, a little bit mathematical, I would say. But it's an important, important thing, probably the most important effect in nonlinear optics at all, namely second harmonic generation. So we will look at the coupled wave equation for second harmonic generation, and we'll solve them. It turns out that this is not so, that this is a little bit involved. I think that you should see it once, but you probably, you should perhaps remember one of the strategies that we use to solve that, because you might need them for other applications. But besides that, I think the only interesting thing is the solution. And therefore, and also because this calculation is lengthy, pretty lengthy, I will present it again here on as a PowerPoint presentation, or rather keynote presentation. So you can relax, and you would just remember the important points here. Okay, so let's look at that. So the next chapter here, this is the mathematical description of second harmonic generation. And the first thing that we would do is to derive the coupled wave equations for second harmonic generation. Right? Ignore the first point that I wrote here. We start right away with the second point here. Right? Which means that we decompose the field into the fundamental and the second harmonic. So just superposition principle, nothing more. So this here oscillates at the fundamental, this here oscillates at the second harmonic. And then we would do what we typically do, namely that we factorize the spatial dependencies and the temporal dependencies, which is possible if the amplitude increases slowly as compared to the oscillation. So if the oscillation is much, much faster than the amplitude, then you can do this. I should mention here that we can produce, so with our lasers down in the first on the first level in my labs, for example, we can produce laser pulses that consist just of 2 or even less optical cycles. Then the slowly varying amplitude approximation would not be valid, right? So you need fairly long pulses consisting of, many cycles, whatever many means. So it's just a question on how good your approximation should be. Good. The dispersion relation is also obvious, right? And then we just copy this equation that we used before. So this is this driven wave equation. We have to find an expression, of course, for the source term, right? And there is, of course, the source term for the second harmonic. But we also know that it is possible to, or that it may be possible, we consider it actually as very probable, that the second harmonic may actually be back converted into the fundamental. So there should also be a polarization at the fundamental, right? And this is actually the next point that we have to consider. Yeah, so what the nonlinear polarization at the second harmonic is obvious. So look back into chapter 2. There we derived an expression for the polarization. The only difference here is that we use, instead of the susceptibility, the effective nonlinearity, right? And we'll look at this a little bit later, but basically it's the same thing, right? The question is now how to get the nonlinear polarization at the fundamental, right? And the trick is that we say, well, this is some frequency generation, namely of the second harmonic and the negative fundamental. All right, so omega 1 is 2 times omega 1 minus omega 1. Isn't this trivial? So we again go back to chapter 2 and look for the respective polarization and exchange the susceptibility by the effective nonlinearity and perhaps this factor of 2 that appears there also, and that's it, right? And then we find this polarization here. So you see it here, right? And this is the one that I mentioned already. And now if you substitute the ansatz here, yeah, so the wave, and these two polarizations, if you substitute this into this equation, where is it here? 5, right? Then you get the coupled wave equation. Yeah? Unfortunately, this was the easiest part of the entire thing. Now we have to solve it. And if you are looking at complicated differential equations, then it's always a good strategy to make them dimensionless, one thing. And the other thing is to look for conserved quantities. Yeah? And both of these things is what we are going to do. So the first step would be to make these equations dimensionless. And we do this by dividing, well, actually, we go a step further. Yeah, so what we also do is that we write this this complex quantity. We write it as a product of the magnitude and the phase. Right? It's of course clear that u1 as well as phi1 are now real functions. And we decorate it with this factor here, yeah, such that u1 is dimensionless. Right? This here is dimensionless anyway. Right? And we do the same thing with amplitude A2. Yeah. So the intensity, this is the total, so I is the total intensity, which is the sum of both intensities, right? And this already gives us a first conserved quantity, namely u1 plus u2, this is equal to 1, right? So u1 squared actually, yeah? So we're talking about the intensities, u1 squared plus u2 squared, this is equal to 1. A first conserved quantity here that we will use in order to decouple both equations. Yeah, so you see that we have now a relation between, an implicit relation between u1 and u2. And this can, of course, be used in order to decouple a system of equations. So we also make the argument. So I said u1 and u2 are dimensionless, but the argument is not yet dimensionless. So it makes a lot of sense to make them also dimensionless. And this we do by introducing this variable zeta, so which is equal to z divided by L, and L is defined by this yeah, by this lengthy expression. Right? I once did it and looked whether this really is a dimensionless, whether this L really has the dimension of 1. So my pointer is gone. That would be a pity. Yeah. Let's see whether we can revive it. Okay, anyway, what you see is that we have now this at least I have a pointer here. It's not so fancy than the one I had before. But anyway, better than nothing, isn't it? If we did this, then we can also, of course, transform the differentials so that I can also write for the differential here for dz something dimensionless. Okay, so I have an inconvenient. So now I've got an Ansatz. Yeah. Monster pointer, huh? Okay, so I have an Ansatz and I have the coupled wave equation. So what we do? Of course, we substitute the Ansatz into the coupled wave equation. And this is what I, this is what I do here, right? So to be a little bit more specific, right? I have here the derivative of A1, and you see that A1 is a product here of these two functions. So I would use the product rule, and this is actually what I did, right? So I took the derivative of the amplitude and just copied the exponential. And here I do it the other way around. I just copy the amplitude and take the derivative of the exponential. Of course, I have to use the chain rule. Yeah? So this you see here with this factor here. Yeah, and of course on the this is my right hand. Yeah, on the right hand side, I do the same thing. I substitute here A1 and A2. Yeah, so I just substitute here it with equation 11 and equation 12. Good. So there was actually something in the chat, but it didn't ring here, strangely enough. Chatverbindung abgebrochen. Oh yeah, so there's a problem here with the chat, but I hope it resumes at some point. Okay, yeah. So then we use what we did up there, right? So we write this differential here with d zeta, yeah? And if we do so, so I write here d zeta instead of dz, right? And then I have to use, of course, this factor here, and this is what you see here, right? Gets lengthy, right? I have to do the same thing here. But then if you look carefully, then you see that actually pretty much, so that actually all this thing here, so that this factor here is the same than this one here. And moreover, it's the same thing that you find on the right-hand side. You may not see this immediately, but believe me, it's true, right? And so, if you use this, then you can write this monster equation here in this fairly handy equation, right? We can collect all these exponentials into one exponential. This is what I did here. And next I just define an abbreviation. Instead of 2 times phi1 minus phi2 plus delta k times z, I just write theta. It may be worthwhile to think a little bit about this phase phi1 and phi2. So it's no accident, well, there's never an accident in physics, but it's what you expect, of course, that the fundamental, if you subtract, so the phase of the fundamental, if you take it if you multiply it with a factor of 2, then it changes as quickly as the phase of the second harmonic, right? And then, yeah, so then you realize what this here, yeah, delta k is the phase mismatch. If this is 0, right, then you see that both colors are in step lock, so to say. So let's hope that it has enough electrons. Meanwhile, this remote, it would be nice if it would again produce. So we have to live with this ugly arrow. Anyway, yeah, so this is one of the equations that we'll work with. So we'll change here this expression. So we'll just write here theta for this here, and then we remind ourselves of Euler's formula, namely that the exponential of minus I times alpha is the cosine minus I times the sinus of the argument, right? And this is what I just wrote down here, right? So same thing here. Yeah, so nothing has happened, just the complex exponential function was written using Euler's formula. Good, yeah, and here I multiply it out, and then I do what you probably expected when I started to make this ansatz where I factored the amplitude and the phase. Right? So at one point, so this is what always happens if you do something like that, that you compare, that you say, here I have actually 2 equations. So this equation must be fulfilled for the real part and for the imaginary part independently. Yeah? So this is, yeah, so you see this exclamation mark in red. So this is an equation that we'll remember. Yeah? It's always good to remember what we are actually after. So we said, we said that we have the coupled wave equations, and we said that we want to make them dimensionless. And here you see the first one of these dimensionless coupled wave equations. Yeah? They are still coupled, you see, right? Actually, they are coupled in a pretty nasty way. Yeah? So it's not only not only the amplitudes are coupled, but also the phase is mixed into it, right? Okay, so far we substituted our ansatz in the first coupled wave equation, and so it's obvious that we now would substitute the ansatz into the second coupled wave equation. This is what I do here, and I do pretty much or more or less exactly what I did with the other, with the first one, right? And you see that we get a similar equation. Yeah, so we get a similar equation. Well, it still has the structure of the coupled wave equation that we had initially. We'll compare them later once again. Right? So what you see here is the amplitude of the fundamental squared, here dimensionless. Right? And this has to do with the spatial change, so with the change of the amplitude as the wave propagates. Right? So theta is the normalized propagation distance, and what we see is here how the second harmonic grows as it propagates through the nonlinear medium. Okay, yeah, so I said these are the two important equations, and therefore I remove all the other stuff here. So we go on with these two equations, but remember, so far we just looked at the real part. We can also look for the imaginary part, and this is actually what we do next. Yeah? So you see, we had two coupled wave equations, and now we have four. I said I make it simpler, right? 4 instead of 2. Well, the ones for the imaginary part will be consolidated into one. So a third equation from the imaginary parts. I take the imaginary parts. Yeah, so here is still the equation from which I took so far the real part. So I took this term on the right-hand side, and I took this term on the left-hand side. And now I take the phases, right? And what I find is this equation, and from here down, from the analog for the second coupled wave equation, I find this equation here, right? And now it gets tricky, right? And I'm pretty sure those who found that out for the first time, that they also worked for a few days on it. I probably would work for a few weeks on it. Oh, well, perhaps not, but okay. Well, so we do some tricks. Yeah. So what we do is that we calculate the derivative of this abbreviation theta. So remember theta, what was theta? This was 2 times the phase of the fundamental minus the phase of the second harmonic, and then the phase mismatch, right? Ah, yeah, here it stands actually, all right? So this was given by equation 18. So if we take the derivative, then we find this expression here, right? And now we substitute these two equations that we got from the imaginary parts of the dimensionless equations. Yeah? So we find this thing here. Yeah, so we substitute equation 23 and 24 into this equation, and we find this, this thing here. More tricks now, right? Even trickier, yeah? Much more tricky, I would say. So what we do here is that we calculate the derivative of the logarithm of fundamental amplitude squared times second harmonic amplitude, right? And if we do this, yeah, so you see chain rule here, the derivative of the log is of course 1 over this argument. This is what you see here. And then we have to use the chain rule and apply the product rule. This is what you see here. Right? And this can be, yeah, again, we can substitute here these equations. Yeah, so equation, actually equation 20, so these equations here. Yeah, so we can substitute these equations here. And we find this expression here. Yeah? And these are now the dimensionless coupled wave equations for second harmonic generation. Instead of 2 equations, we have now 3 equations, and it will now be the our goal to find solutions to that. Okay, well. Once again, what will be the strategy in order to decouple such equations? Once again, we'll use conserved quantities. One we already have, namely that u1 squared plus u2 squared, that this is equal to 1. But this is of course not sufficient in order to decouple 3 equations. There we need another conserved quantity. And this means that we need another trick, right? And we'll do this after a short break. You may see or hear already my boiler, so I brought a cup of tea here, right? My favorite institute here, the Helmholtz Institute Jena. And I hope you also have prepared a coffee or a tea and maybe some Christmas cookies. And so we'll have 3 minutes or 5 minutes. It takes actually 3 minutes for the tea to be finished. And then we try to solve these coupled wave equations. The chat doesn't seem to work any longer, right? So. I should have prepared it earlier. A little bit hot. Okay, this is good enough. I could try it out, this chat here. Let me try this chat. No, it doesn't work. I get an error message. I don't know how to fix it. Good. So everybody a little bit relaxed. So now I got a ping here. I try it once more. No, doesn't work. I'm sorry for that. So let's go on with the lecture. So we want to decouple this set of equations. Decouple this set of equations that we have here. So 29a, b, and c. So, and I said, remember, conserved quantities is a good strategy. And we actually do the decoupling by assuming that we have perfect phase matching. Otherwise, well, it can also be solved, but not with elementary functions. So, as I said, so one of those of conserved quantities we have already. And for identifying a second conserved quantity, we prove that this expression here is equal to 0, right? Similar to what we had before, but different. a little bit at least. So same thing, right? Derivative of the logarithm 1 over the argument, and then we have to use the chain rule and take the derivative of that, and this means that we need to use the product rule, right? And then we end up with this expression where we have the derivative of theta with respect to zeta, right? And for this we substitute here this equation 29c. And if we do this, then we see that these trigonometric functions, that they cancel, right? And we also see that these two, well, that this here cancels with this, and this here cancels with that, right? And we see that this is indeed equal to 0. So this means that this here doesn't, so that this expression here doesn't change, as we propagate through the crystal, right? So remember, this is amplitude 1 squared, amplitude 2 of the second harmonic, and this somehow, in some way, the phase, right? And this combination doesn't change as we propagate through the crystal. Nice, right? So it's constant, so, and this means that we can write gamma for it, right? So this is what you see here. So we have found two conserved quantities. Actually, it would be possible, knowing the initial conditions, so knowing the amplitude at the position z equal to 0 and the second harmonic at the position z equal to 0. Usually the second harmonic at the position z equal to 0 will be 0, but not necessarily. Yeah? If not, then you would also need to know the phase of between both. Yeah? And if you know these initial conditions, you can always calculate gamma. Yeah? So gamma is in principle known. Okay, so what next? Yeah, now we start to decouple both, right? And this goes in a way that you would expect, right? So here we have these two quantities, right? And we would try to eliminate one, right? And we eliminate, in this case, U2 by using the first conserved quantity. We said that U1 squared plus U2 squared is equal to 1. So U1 squared is 1 minus U2 squared, right? And here we do a similar thing, right? We also use the Pythagorean theorem here. So then we have here the cosine squared, right? And for this we can use this equation that we just derived, right? And then it can be a little bit rearranged. So you see that that we bring this under the root here, such that it simplifies. Actually, there's not much simplification so far here, but we do this here once again, right? So this trick so that U1 is really eliminated. So our equation 33 contains only U2. That's nice. Yeah? This is a differential equation that can in principle be solved, but it's not an elementary function. So these are the Jacobi elliptic functions, which are double periodic functions. And well, that they are periodic is already a good sign, right? Because you have a back and forth exchange of energy between both waves. But we won't do that. Yeah? Actually here, a reminder of our coupled wave equations. Okay, now we try to solve the coupled wave equations for the special case that gamma is equal to 0, and we'll see that this case is actually not so special, because we said already that we use the special case where we have perfect phase matching, and it will turn out that gamma equal to 0 is pretty much the same as perfect phase matching. Yeah? And the nice thing about gamma equal to 0 is that we find a solution in terms of elementary functions. Okay, what does it mean if gamma is equal to 0? Once again, gamma was defined as u1 squared times u2 squared times the cosine of theta, and gamma can only be 0 if one or several of these factors are equal to 0. Right? Okay, if u1 is equal to 0, then this is probably not a very interesting case, because it just means that you don't have a fundamental, and then you probably also won't have a second harmonic, at least not for finite distances. Well, moreover, if you think about continuity of these functions, then it's clear that that if there won't be a coordinate z or theta at which, say, u1, if u1 initially is equal to 0, right, where it switches to u2, right? So if u1 is equal to 0, then it will be 0 for the entire propagation. Yep. So all this says that the cases where u1 or u2 are equal to 0, that they are trivial cases, right? So we can concentrate on the case where the cosine of theta is equal to 0, right? And this means, without much loss of generality, that the sinus of theta is -1, right? Could also be +1, but this is the case on which we concentrate. Yeah? What does it mean? Yeah, what's the physical meaning of that? And this is actually also the justification for this choice. The meaning is, yeah, so if you look at that, then you find that you have a phase difference of 90 degrees between both colors. And now think again on which problem we are dealing with. We are dealing with the problem where we kind of have where we have a driven wave equation, and we want to transfer energy from one wave to the other wave. And if you think about the analogy of a driven oscillator, then you know that the driving force has to be, or that the driving force transfers the maximum power to the oscillator if both have a phase difference of 90 degrees. And this happens at resonance, right? And we are kind of have the resonance case here also, because omega 2 is 2 times omega 1. Right, so with this analogy, it should make sense what we see here. Okay. Yeah. So this is what I just tried to explain. Okay. So if this is the case, then these dimensionless coupled wave equations, they look a little bit simpler. right? And I guess I missed here a minus sign. Yeah, so I said that sinus of theta is equal to -1, so there should be a minus sign here. Here it's okay, right? And we already assumed that this delta S is equal to 0 because we said we want to have perfect phase matching. And well, and now we find that this here is equal to 0. Yeah, and then decoupling is actually trivial. Yeah? After all these efforts, we find then, so we can easily decouple these equations. We just have to, so I did it here, right, for this one here. And this has an easy solution, you just need to look it up, or you actually know it. And what you find is that the amplitude of the second harmonic goes like the tangent hyperbolicus of the propagation. Well, there's also a coupling, a constant of integration. And if you use, well, say, natural initial conditions where the second harmonic is 0 at the entrance phase of the crystal, and we say that the entrance phase of the crystal is at the coordinate zeta equal to 0, then we find that this zeta 0 is equal to 0, right? And then we have this nice this nice solution for the second harmonic. Okay, now same thing for the fundamental, right? So for this we, so I should go back perhaps. So we now use this equation here once more. And what we find here is, so that we have the derivative here of u2. So we have to take the derivative of the tangent hyperbolicus, and this is the secans hyperbolicus. Yeah, 1 over the cosine hyperbolicus squared. Yeah, secans hyperbolicus squared. Yeah, and now it's time to just plot that. We can, of course, also undo the normalization. Yeah, so go to dimension, to quantities that have dimensions again. Right? So we can undo all these things that we did in the beginning, right? And what you see is that the fundamental gets depleted, yeah, and goes actually to 0 asymptotically, right? Whereas the second harmonic eventually, of course, also saturates, yeah, because if there are no more photons available for the from the fundamental, then of course the story is over. But you see, in principle, it's possible to convert the entire energy, so all the photons from the fundamental to the second harmonic. And we have shown it analytically. Isn't this nice? Yeah. A final step to do. I'm actually faster than I thought. So we can stop a little bit earlier today. An example. So what we want to do is to estimate the conversion efficiency. Yeah? And so what we said is that in principle we can convert the entire energy to second harmonic, but we'll see that in reality this is actually not so easy. So we start with defining the conversion efficiency, and the natural definition is, of course, that you say how many percent do I convert, right? So in other words, I take the intensity of the second harmonic after the crystal, at the exit phase of the crystal. If the crystal has the length L, then I would take it at the coordinate L. And I divide it through the intensity at the entrance phase of the fundamental. A natural definition for the conversion efficiency. So this is in terms of the coordinate z, right? So I wrote it so far in terms of the coordinate zeta, and so we have to convert that back. So we said that zeta is defined as the coordinate z divided by this typical length, this length scale, and now we say how big is zeta at distance L, right? So we just need to substitute here z by L, and you see that we get this term here. Looks complicated. Well, it was a little bit complicated term in order to define this the scaling of the propagation distance. Well, what we see is that the conversion efficiency depends of course on the intensity. We know this since a long time, but it also gets evident here. And what we do is that we estimate the intensity by the intensity of the incident fundamental. So you have a laser, which is the incident field, and you measure its power with a power meter. This power meter displays so and so many watts or so, or milliwatts. But you need the intensity, and therefore we divide it by the beam, by the cross section of the beam. We said that we need high intensity, so what we generally will do is to focus into the nonlinear crystal, in order to have high enough intensity. And now you could say, well, I can focus very tightly. So I have a crystal of length, say 3 centimeters or something like that, right? And now I take my laser and just shine it through. No harmonics come out, so I decide that I focus it, right? And because I know that it goes with the intensity, I decide to focus it as tightly as I can, right? Question is this a clever thing to do? Well, if you focus very tight, then of course also the length of the focus, so the length of the volume where you have high intensity decreases. Right? So it doesn't make sense to make the crystal longer than you make the focus. Right? So what you see here is that, or what we will see, or what is actually evident, is that the conversion efficiency increases if you increase the length. We also see that it increases if you increase the intensity. So you have to find a compromise. Right? And if we talk about just estimating things, then we can say, of course, well, we choose the crystal length to be twice the confocal parameter of a Gaussian beam, right? So because the confocal parameter of a Gaussian beam, this is kind of the length of the focus. this is where the intensity has not dropped considerably. Well, it drops considerably by a factor of square root of 2 or so, but not too much, right? Okay, what we say is, so therefore we demand that the crystal length equals twice the confocal parameter. So 2 times this Rayleigh length is this confocal parameter, and this should be equal to the crystal length capital L. And for confocal for a Gaussian beam, the confocal parameter and the beam waist, they have a well-defined relationship, right? So this is used here, and in this sense, I can write the intensity in terms of the power and the length of the crystal. Right? What also comes out is that, what you also see here is that we find here the wavelengths. So the shorter the wavelengths, the larger this will be. Okay, now we can write zeta. So equipped with all of that, we can write zeta in terms of the length of the crystal and the power of your laser, and you find this equation. Right? Length of the crystal, power of the laser. Well, we also need the nonlinear coefficient of the crystal. How do we know that? Well, we would look into the catalog of a company that sells these nonlinear crystals, or we would look in a later chapter here and perhaps do it ourselves. Okay, so let's discuss it. We said this already. Power helps. So what we see is that it just goes with the square root of the power, right? So what you see, and the reason is, well, we have that the tangent hyperbolicus is initially linear. So this means that the intensity is quadratic in zeta. However, in the long run, this the intensity becomes linear in P. Right? Short wavelengths, I mentioned it already. This also helps. And now a numerical example. I take a green CW laser. Right, would frequency double it, so then I would arrive actually in the UV, and I take something with a watt, 1 watt of power. Right? So nowadays you can buy such lasers as handheld lasers, probably forbidden, depending on what you want to do with it. We take a crystal of length 1 centimeter, 10 millimeters, right? Refractive index doesn't depend too much on it, so you can assume what you want. Something on the order of 1, and a typical order of magnitude for non-linearities that are instantaneous, that are lossless, so that are typical for electronic processes, so for fast processes, in other words, instantaneous processes, so that we have a parametric process here. Right? Then we plug in everything, right? We find zeta equal to 0.18, right? And now if you substitute this into this equation, right, then we find just 3%. I promised 100%, didn't I? So you have to do things differently. So 1 watt is definitely not enough. So what you should use would be a pulsed laser, right? So the only thing that matters here is, of course, not the average power, but it's the instantaneous power. Right? And now if you take a nanosecond laser with an average power of 1 watt, nanosecond, you get already gigawatts, right? So this is perhaps already too much, right? So you probably don't need to focus it that tightly. Yeah? So there's a lot of room above. Yeah? So getting this power here up by many orders of magnitude is not the issue. So this was second harmonic generation. I'm really unhappy that the chat didn't work today, but I can't change it. I still hope that at some point I can have a Zoom session here in parallel. In principle, this should be possible. We don't do this, so we prefer YouTube actually because the quality on YouTube is much better than on Zoom. Yeah? So my handwriting, or also the slides here, if there's a lot written on them, wouldn't be easy to see on Zoom. So this is the reason why we use YouTube. But actually, in the near future, I hope that we have a parallel Zoom session. But for next Monday, as I said, I would like to invite you to a Zoom session. Yeah, so just Zoom, so where you can ask questions, make comments, or just chat on whatever you wish. So with this, see you next Monday. Thank you.